Hey, welcome back, everyone. We'll go ahead and get started here. It looks like 7:30 according to my clock, so close enough. Appreciate everybody coming back, and we're going to take a little less theoretical journey this evening. It'll look a little bit more at weather maps, soundings, not so much the concepts behind it, but we're going to be applying that this evening, and hopefully you'll see why it's important to go over that stuff before we get to this. So tonight we're going to focus on low-level moisture return, the sources for the moisture, and then we'll follow it up with a discussion of temperature lapse rate sources, primarily in the mid-levels of the atmosphere. So there'll be a lot of stuff to cover, but it should be a pretty interesting presentation, I hope. All right, just to continue the trend from week one, showing you where we are in the workshop organization. This is the second session. Again, the first where we'll deal explicitly with severe thunderstorm ingredients. And we'll follow that up next week with the other two ingredients, which will be sources of lift and vertical shear. So we'll revisit some of the synoptic meteorology stuff next week as well. All right, low-level moisture in the return flow cycle. It's pretty straightforward, but I'm kind of surprised how few people actually look at it very much. In this case, it's just what happens to air as it moves over a relatively warm ocean surface, and then where does the air come from when you trace it back onto land. Sounds pretty simple, right? Well, it is fairly simple if you actually follow the air the whole time, but the problem here is this takes upwards of a week before a severe weather event, so you have to keep track of things on a daily basis. First thing we want to do is look at the Gulf of Mexico basin. This is a series of plots. There in the upper left is the estimate of the mean sea surface temperature for the Gulf of Mexico for the entire year. Of a little more interest will be on the upper right. We're looking at the annual curve of the mean temperature, sea surface temperature for the Gulf Basin. And as you can see, we're near the min seasonally. Usually it's sometime between now and the beginning of March. And I just highlight where we are. And you see those water temperatures on the order of 23 C. So the Gulf Basin doesn't get that cold in the cool season, but definitely it's cooler than you see in the summer. So there's about a 7 C cooling from the peak in late summer to about now. Well, look at the bottom. We've also got a series of all the interannual variations in the Gulf sea surface temperatures. You hear a lot of people talk about, oh no, this one frontal intrusion, boy, that's going to really wreck the Gulf. Well, if you look at the two blue lines I've highlighted there, that's a range from about 22 to 23 C, so about 2 Fahrenheit range is all that is. Almost every year, the peak, the min sea surface temperature falls in that 2 Fahrenheit range. So what it says is that this doesn't vary greatly from season to season. There are variations, and I'll highlight some of them, and perhaps some of them matter. Here's a case where it was a warmer year. This one was 2005. Not the biggest severe weather season, so I wouldn't say there's the strongest correlation there. Move a few years later, 2008. That was a big tornado season out in the central U.S., and once it got active, it stayed active a long time. You'd say, okay, well, maybe there is some sort of cause and effect. 2011. One of the coldest of the recent years. I don't think you're going to do very well if you're going to say, well, the Gulf's too cool, we shouldn't have much in the way of tornadoes or severe thunderstorms this season. That would have been a pretty poor forecast in the spring of 2011. So point here is the sea surface temperatures respond on the order of weeks and months, and really all it is a reflection of the pattern you were in before the time you're interested in. Doesn't necessarily mean a whole lot once you come up to a specific severe weather event. Okay, here's the Gulf of Mexico. This is a fairly recent sea surface temperature analysis, maybe here within the last week. The yellows there, that's temperature 24 C, so you're in the 70s. The waters out in the open Gulf stay in the 70s all year. And what I've done on this image is I'm placing, if you convert the sea surface temperature to what you could call the equilibrium dew point. So essentially, if you just let air float around over the ocean surface, at some point there ends up being basically a radiation balance between the air and the ocean, the amount of mixing due to the wind, and you end up with relatively steady conditions. That's why the tropics are so stable in the sense that the temperatures and dew points don't vary wildly day to day. So in this case, low 60s, mid 60 dew points across the Gulf Basin now. So in this case, if you want to see dew points in the 70s, it's not coming from the Gulf Basin this early in the season. Now you get toward May and June, totally different. The water's quite a bit warmer. So this is just something to keep in mind. you can actually look at a sea surface temperature analysis and predict what's kind of a high-end dew point that I would expect to find if I give sufficient time for the air to modify over that ocean surface. The other thing you need to keep in mind is there's a lot of variability in these contours. If you look at this, that little chunk of warmer water south of Louisiana is known as the loop current. It's actually west of its normal position right now. Little eddies will break off and move around for months across the northern Gulf. And the Earth's crossing changing sea surface temperatures all the time. So I think in the cool season, there's a misconception that, well, you know, the Gulf moisture, really you want good moisture this time of year, it's Caribbean moisture. So you need trajectories coming from the tropical oceans, not so much the northern half of the Gulf Basin. All right, now we're gonna look at a full bore return flow case, start to finish, in gory detail. Hopefully it's not the most detail any of you have ever looked at, but if so, welcome to the world of moisture return. Okay, the area highlighted. This is the dead giveaway of strong air mass modification. Tremendous heat and moisture fluxes going on over the north central Gulf. You see the cloud streets. You see that inland with some regularity during the spring and summer in the warm sectors, but in this case, this is driven by very strong moistening and warming of the surface air. That's cold continental air moves over the temperatures in the low 70s, it warms up very quickly. And that's convective mixing. It's the same thing we looked at last week, except in this case, instead of driven by daytime heating, it's warm ocean temperatures. Now what I want to do is something I don't see people do too often, so that's why we're going to do it. We're going to look at all these sounding sites around the Gulf Basin for the duration of this return flow cycle. Starting down in Cancun, and then we'll move around to the extreme southwest Gulf of Mexico, which is Veracruz, continue up to Brownsville, Lake Charles, and then Tallahassee, Florida. So we're going to kind of surround this whole return flow regime and see how the profiles change on a 24-hour basis. All right, and then what we'll do is we'll also follow the same order each time. I'll start at Cancun, and we'll go around the clockwise around all of the stations in the order I just listed them. Okay, here's Cancun. You notice from that analysis, they're very close to the frontal system that's moving through the Yucatan Peninsula region, Northwest Caribbean. It's moist, it's a somewhat tropical looking air mass. This is essentially right in the frontal zone, so nothing too surprising there. We'll see how it changes over time. Moving back to the west, Veracruz, clearly this is one that has experienced some cooling and drying in the low levels. You may see some influence of the terrain with that moist layer above the surface. Continue up to Brownsville, definitely cooling and drying compared to the prior frontal intrusion. You notice that it's nowhere close to being unstable. The surface lifted parcels, there's nothing close to any cape except maybe in the little scrawny layer around 850 millibars. And then of course Lake Charles, very dry continental air, cool, and the same thing at Tallahassee. Okay, so this kind of sets the stage. This is the offshore flow air mass modification phase. Let's jump ahead 24 hours. And just to keep in mind, the satellite pictures I'm showing here, those are from 18Z. All of the soundings are 6 hours later. So this is just to give you an idea how the pattern's evolving. Okay, in this case, the initial surface ridge has moved down toward the Mobile, Alabama region, or Pensacola, Florida, somewhere in there. We do have some weak return flow already into the Texas coastal plain. Winds have come around to south. But I've traced out just a snapshot of the streamlines in the airflow. So in this case, you get the impression, comparing it to the last map, that the air that is moving into Texas is coming across the northern Gulf. So it's not moving over the warmest water, and it has not been over water for long. Okay, we'll look at the soundings. Now, just so you are oriented here, this is Cancun 24 hours later. In the background is the previous sounding in purple. So that was 24 hours ago, the same sounding location. So you can see in Cancun, we've dried and cooled in the low levels, especially just cooling. It's still not particularly cold. And again, this is about where that frontal zone stalls. Veracruz has already shown signs of moistening, and this is a response to the long fetch of post-frontal air across the entire Gulf of Mexico from northeast to southwest. Very moist, but again, it's not an unstable profile, it's just moistened. Brownsville, quite a bit of moistening has occurred. You see in the green, that's a fairly deep, moist layer, but again, notice compared to the mid-levels, there's no buoyancy in this profile. It's moistened, but it's a deep moist layer, but it's not sufficiently moist. Lake Charles, same thing, rapid moistening, tremendous, almost 15 to 20 C increase in the dew points at Lake Charles from the previous day. However, very warm mid-troposphere. Essentially, this tells you the influence of the cold front was all down in the low levels, below 700 millibars, but the air in the mid-troposphere didn't change much. So we're going to need to moisten and warm quite a bit to get any buoyancy in this profile. And still offshore flow at Tallahassee. Okay, so that's 24 hours worth of change. Let's jump ahead another day. Same sort of thing. The high hasn't moved too much. It's sitting kind of anchored near the northeast Gulf Coast. I know it's hard to see on this screen. The greens, those are dew points in the 60s into South Texas. Again, trajectories or implied trajectories are coming out mostly out of the east, so they're coming across the relatively cooler part of the Gulf Basin. We're not getting the maritime tropical air. That's still tied up down in the Northwest Caribbean. All right, let's look at the soundings. Now, Cancun is already starting to modify. They've got a long east or northeast flow along the frontal zone. The water down there is pretty warm. It's crossing 80-degree water. It modifies very quickly. Surface dew points are already up around 70. We're already starting to lose the influence of the front there. Veracruz, interestingly, hasn't changed much. Flow was out of the northeast, and now it's just weak southeast flow. It's essentially in that same part of the trajectory where it's the air that's milling about in the southwestern Gulf. Hasn't changed much in 24 hours. Brownsville continues to moisten. Again, now we're starting to see at least a little bit of Cape. We've also cooled some in the mid-troposphere. And in this case, we're starting to set up the early stages of an unstable warm sector. Not much change at Lake Charles. And we've shown a little bit of moistening at Tallahassee, but essentially it's still the offshore flow phase over there. All right, day 4. No big change in the trajectory. So in this case, you wouldn't expect a huge increase in moisture anywhere. If you're just following where the air is coming from, the tropical air is still tied up down to the southeast. We're still bringing air off the southeastern U.S. part of the continent across the Gulf Basin into Texas. So again, it's no rapid change would be expected in this regime. Cancun is essentially fully tropical now, low 70 dew points. They continue to slowly moisten down there. Veracruz, interesting drying just off the surface. And this is a good example of why you need to look at the soundings and not just assume. You could say, well, it looked moist yesterday, I don't expect any change. I don't actually have a good explanation for that drying in the layer, but the surface dew point looks like it didn't change from the day before. So unless you look at the vertical profile, you wouldn't necessarily know how important the changes in the moistening were. Brownsville, same sort of thing. There's a lot more complexity now. Perhaps this suggests that we're not in the active modification phase anymore. Everything's kind of achieving some sort of balance because now you see a couple of different little layers below about 700 millibars. Again, it's difficult to explain exact origin of these because we have so few observations upstream. But again, it has not moistened substantially from the day before. Lake Charles, same sort of problem, not much change yet because they're not really in the onshore flow phase. And then Tallahassee is, with the ridge still sitting there, nothing much has changed for them. All right, day 5. Now you look down in the southern Gulf, it looks like we have the old tropical air masses essentially flooding back into the southern Gulf Basin. And notice there's the lack of clouds down there. You don't see all the stratus or anything, and that's a reflection of a fully modified air mass. Where you see much more in the way of cloud cover, we're probably, in this case, we're bringing higher dew points over cooler water temperatures, all sorts of things going on. But the tropical air is just to the south, but we're still in that trajectory coming into Texas. It's air that's, again, not too much different than the previous days. Now, in this one, we were missing the Cancun sounding, but it doesn't really matter. They're down deep in the tropical air. Veracruz is now starting to look almost tropical with a low 70 dew point. 71 degrees is what that is at the surface. Looks a little bit like Cancun did the day before. Brownsville, the moist layer, again, it's a little more complex than that first day. We don't have the strong heating and mixing anymore, and dew points are in the 60s, but it's a relatively shallow layer, so there's some question as to what that would look like as you came further inland. Again, the details may be important. Lake Charles, we've moistened quite a bit from the previous day. In this case, we're in a warm advection regime there, as noted by the strong veering wind profile. And there's precipitation formation not too far to the east of them. And if you go to Tallahassee, this is actually tangled up in a lot of rainfall and some elevated thunderstorms over the northeast Gulf Coast in a very strong warm advection profile. All right, this wasn't the most dynamic system in the world, but it did move across the northeast Gulf Coast with some severe weather the next day. Now, if you look toward the northeastern Gulf of Mexico, if you can, I don't know if you can read the numbers, I should have highlighted it. There's a couple of buoys. The one that's just south of Apalachicola has got a 71-degree sea surface temperature, but the dew point there is 72 degrees. It should be crystal clear that air did not come from anywhere close to that buoy location. That's Caribbean air in the low 70s that's flooding up into the Florida Panhandle. Of course, it's also a relatively cool air mass as we get inland, so there's a lot of saturation and cloud cover. All right, we'll just focus now. We'll give the time series for Brownsville just to give an appreciation for what it looks like when it changes. This is the first day post-frontal. We've cooled. It's not dry, but it's cool and relatively moist, but stable profiles. The next day, as soon as the winds turn around, we've got a fairly deep moist layer, but again, not unstable. Day 3, now we're starting to look something like a warm sector sounding. Again, the storm track is still a little bit far to the north at this time. But if you notice over the next 2 days, the moisture doesn't just automatically get better. It doesn't just increase magically every single day. And I have a fun case later. Just keep that in mind. All right. Now this is one, I'm not going to ask you to answer this. I just want you to sort of think about it based on what we've been talking about here. This is something we can talk about it in the break if anybody's interested. Think about what kind of air mass modification you would expect in this scenario. What I've done in the orange is I've highlighted the air temperatures are in the 65 to 70 range, and the sea surface temperatures, central and southern Gulf, 72 to 74. Notice there's not a lot of cloud cover. It doesn't look like the previous one. Just think about what would be happening in that boundary layer. Is it modifying rapidly or not? And what does that say about the potential air mass and moisture return in advance of the next weather system? Okay, now you figure I can't go too long without showing a more interesting case. You know, the other one, just a little bit severe weather. We finally got to get something with a little more substantial that occurred. I get withdrawal if we go more than like one bad case at a time. Okay, this is preceding the tornado outbreak in Oklahoma, Kansas back in April of 2012. This is going to be a 7-day sequence preceding that. So first of all, you notice there's already dew points in the 60s across the southern half of the Gulf Basin, even 60s up into northeast Texas. The dark green is 60. The light green in the southern Gulf is a 68 dew point. So this is just straight off the SPC mesoanalysis graphics. Day 2, we keep the same sort of pattern, not too much change. Again, there's no strong frontal intrusions noted. Day 3, dew points, even though there's offshore flow in the northeast Gulf Coast, the air quickly comes around to easterly. So we're not changing the trajectories very rapidly. Day 4, same sort of thing. If you looked at the larger view, there's actually sort of what some people might call a backdoor front that runs from Oklahoma down toward the northeast Gulf Coast. Again, that does not make any deep penetration into the Gulf Basin. South of that front, we've just got long east and southeasterly fetch, and this is actually 48 hours prior to the severe weather event. So we've already got mid-60 dew points on the Texas coastal plain and richer moisture upstream. So again, these sort of moisture returns are no big shock. It's not one of these like, wow, where did these high dew points come from? This is something that should have been apparent days in advance. Okay, day before, 24 hours out. Now we've got low 70 dew points into the western Gulf Basin and mid-60s all the way across the Red River. This is the sort of scenario you would like to see if you're trying to forecast some sort of major severe weather episode, in addition to other factors. And of course, here we are, day 7. This is essentially go time on the event. Mid-60s have spread all the way into southern Kansas. And again, there are no real rapid changes. So this evolved very slowly over the course of a week. And it's just a matter of paying attention to what's upstream. And I'll show the same sort of thing aloft. We'll just look at, since we hadn't done that with the other case, let's look at what happened at 850 millibars. So this will give us some idea off the surface what's occurring. This is, again, same day 1 to day 7 evolution. Again, this is not a very strong frontal intrusion prior to this. There's a low in the northeast, but you don't see a big, strong ridge driving into the Gulf Basin, anything like that. And then I'll just kind of step through it, and you notice that there's no big changes there in the southeast, and eventually we just bring around more and deeper southerly flow trajectories. Moisture's increased into South Texas, and then here we are just the evening of the event. We've 50-knot low-level jet. It's involved with dew points well into the teens at 850, which corresponds to mid to upper 60 dew points in the boundary there. So notice we didn't have a big cold front intrusion or anything. This was a case where we gradually just brought back the tropical air mass for the same time of year. All right, and here's Corpus Christi. We're going to look at the sequence just like we did with Brownsville. This is down in the corridor of the main moisture return. This is essentially the day right around frontal intrusion. So we have some drying, a little bit of cooling, but mostly drying at Corpus Christi. And again, we haven't done too much at this point with the boundary there. The air, if you trace the air back, it was coming off the northwest Gulf of Mexico, so the air was not following a very long path over water yet. Now we see the signs of moistening by day 4. We've got dew points well into the mid-60s. Now you notice the moist layer is not as deep as the previous case because this is actually a reflection of this air mass moving offshore was not that cold, so the mixing is not particularly deep initially. Now we start seeing something that's beginning to look like your loaded gun sounding, which you would hope to see. This is Corpus Christi day 5. We're still 48 hours out. So again, you're talking about an event up in Kansas and Oklahoma. You better see the moisture down in South Texas well in advance. And again, same sort of profile, moist boundary layer, dew points near 70 at the surface, starting to get the steep lapse rates aloft. We'll talk about that more later. And then the classic loaded gun with a fairly substantial cap, which again, I'll just highlight here. That's what we're talking about, that stable layer, but transition between the steep lapse rates in the mid-troposphere and the moist boundary layer. So we'll talk about that some more kind of toward the end of this session tonight. All right, that's only part of the story. We're just talking about the cool season stuff. Once you get into May, June, that sort of thing, the high dew point air mass is essentially ubiquitous. It's all over the place all the time in the southern U.S. Question is, what happens when you get inland with this stuff? So you have to consider what's the future of the moisture. Okay, we've created a moist boundary layer. We bring it into Texas, for example, if we're interested in the southern plains. What happens to that moist boundary layer as it moves inland? Well, we saw from the last session, there's all sorts of things with vertical mixing. What does it tend to do? It tends to reduce moisture. And if it tends to reduce moisture by mixing dry air aloft down into the boundary layer, we have to offset that with something, which means we have to have horizontal moisture advection. We've also got the problem of what's going on with the soil moisture and the vegetation. Is it dry soil? Is it actively growing vegetation and moist soil? All these things matter. Okay, so here's another spring case that we'll look at. This is one where I just sort of sketched in the temperatures and dew points. And if you remember from session 1, I tried to draw for most of the dew points. Even the AWOS 3s aren't too bad at 12Z usually. Afternoon, different story. But in this case, we have as high as mid-60 dew points into central Oklahoma and pretty continuous down toward northeast Texas. Flows generally out of the south. Okay, 850, so we go up a little bit higher in the atmosphere and look. Flow is a little bit more westerly, but it's out of the south-southwest. Generally, the air moving up into Kansas and Oklahoma is coming from Texas through the lowest several thousand feet of the atmosphere. And there's some hint of moisture and a nocturnal, little lullable jet in the morning. Okay, one thing, we said we got to mention the soil moisture and the impact of this. Here's what was going on according to the drought monitor. This is spring of 2011. This was leading into the hottest summer on record here. And we were already very dry. Extreme drought already across most of the southern plains. What does that say about vegetation? Is it growing as actively as you would normally think? Probably not. Doesn't say a whole lot about soil moisture. So that means chances are we're going to get hot pretty quick and we're going to mix deeply pretty quick, all else being equal. Another thing, here's satellite image the day we're looking at. This is mid-morning. I don't see much in the way of clouds anywhere, so that says something about how close we are to saturation in our boundary layer, which means we're not very close. So in this case, there's not going to be much to slow down daytime heating. It's sunny. It's going to warm up pretty quickly. So what I want to do is we're going to go along this sequence of locations and look at the soundings and see how they change during the day and what impact this had on the potential for any severe thunderstorm activity later in the evening. So we'll start in Fort Worth and work our way northward through Norman, Lamont, which is LMN, Topeka, and Omaha. Okay, so again, this is something to think about while we do this exercise. How deep is it going to mix during the day? What does the moisture upstream from the area you're interested in look like? And what about the soil moisture or active vegetation? I haven't shown anything with vegetation because it was a little bit early in the year for that. But in this case, soil moisture looks questionable down south. And again, we'll go from south to north and look at the changes during the day. Okay, this is Fort Worth that morning. Steep lapse rates in the mid-levels. That's nice. Moist layer looks like it could perhaps use a little assistance, and it's a very warm layer above that. So we'll have to consider that. Now, since we're going to move north to Norman, it doesn't look a whole lot different. If anything, the moist layer in Norman is slightly higher quality than what we see in Fort Worth. So that automatically tells you moisture advection might be a problem today. We're going to have mixing, and we're going to eventually mix down some drier air just above that shallow moist layer, but it's not going to be replaced by much. Okay, so we look at Norman in the evening, and indeed that's what happened. Norman undergoes typical mixing, and if you notice the sounding from 12Z, there's actually more CAPE at 12Z than there is at 0Z. So it's not just a given, oh, it's afternoon, it's going to get more unstable. Not necessarily. And notice this one is very strongly capped profile. I didn't show the outlook for this one, but I think SPC, we had a slight risk that extended down close to here locally, and that didn't work out particularly well. There were some storms a little later, but during the afternoon, not much happened. Okay, now let's consider Norman as the source region for somewhere further north, which will be Lamont. So in this case, similar to the last one, these two are pretty similar. So you wouldn't expect too much change at Lamont during the day. Moisture advection is going to not be particularly strong, and they should show the same sort of mixing signal. Well, in this case, Lamont, fortunately, they launched additional soundings compared to most sites. So this is what they look like by 18Z, which is early afternoon. And then by 0Z, similar profile to Norman. Strongly capped, somewhat mixed boundary layer. Level of free convection is pretty high above the surface. Doesn't look like a sounding that's ready to support convective initiation anywhere close by. Aha, now let's go to the north. We jump up to Topeka, our next spot. This is a different looking profile than what we saw south. The moist layer is deeper. Now notice right at the surface, it's actually cooler than it is down to the south. We're sitting right on that frontal zone. This is on the edge of the stratus that you saw in the satellite image. So we've got something different. This air would be less or more resistant to the impacts of mixing. So in this case, vertical mixing is actually going to bring higher moisture content down as soon as it warms up. So the dew points will jump at Topeka as soon as you get any heating and mixing at all. And there's Omaha, which is downstream from Topeka. Now it shows that sharp inversion with the frontal surface. The moist layer, again, the initial mixing is going to bring higher moisture values down. And if you compare that to the Topeka sounding, you notice that the Topeka moist layer goes up higher into the troposphere than the Omaha sounding does. So this might be a case where you see the opposite sort of thing. Maybe in this case, the mixing and advection will contribute to an increasingly moist boundary layer. And indeed, by 0Z, here's the Omaha sounding. Night and day compared to the other ones to the south. And if you don't think that it made any difference, there's a whole cluster of tornadoes in northwest Iowa that evening. It started just around the time the sounding was launched, and several of these were F3 and fairly long track. So in this case, if you just blindly look at things or consider, well, it's the southern plains, it's spring, winds are out of the south, of course the moisture is going to get better. I mean, that's the sign of a lazy forecaster. If you want to look at all this stuff, you can actually anticipate that the changes may not be what you initially expect. All right, well, there's more. I like moisture, by the way, so we're going to keep talking about it. We have evapotranspiration, and this is one of, again, my favorites in a sarcastic sense because, again, the influence of some of the poor sensors out there. And I've heard all sorts of claims over the years, wow, look at the cornfield moisture and all that. I'll show you a pretty clear example that it's a lot more complicated than simply there's growing corn, and that's why the dew points are high. Okay, but what you do need to consider is if it does make a difference. Corn transpires pretty readily compared to a lot of things, but you get evapotranspiration, you get transpiration from wheat, canola, if you go far enough north into the northern plains and Canadian prairies. You need to have a cap boundary layer to keep the moisture accumulating in that layer, and it needs to generally rain for the couple of weeks in advance. So we want moist soil, actively growing crops, and sunshine. But there's almost always a clear return flow aspect. In other words, the high dew point air comes from somewhere else. Almost the vast majority of it is already sitting there days in advance. Okay, so here's one. Don't worry too much about the details. This is in the morning. I don't expect you to be able to read all the little surface observations, but in general, there's dew points in the upper 60s to low 70s, and focus on Minnesota, Iowa, Illinois. As we go during the day, you notice there's more yellows show up. That's now low to mid 70 surface dew points. The sun's out, it's warming up. And then we go to 0Z. There are occasionally a few spots, some of my favorite observation sites with 81 dew points and those sort of things, which might not be representative of the boundary layer. But we'll just keep in mind, we had some sunshine, and we did get some storms in Minnesota that produced some severe weather that evening. Okay, here's the surface dew point analysis from the SPC mesoanalysis graphics. We'll look at the same time, so at 12Z, 18Z, and 0Z. This one we've got dew points, little spot it claims in the analysis near the Iowa, Missouri, Illinois border of 72 dew points, but mostly upper 60s. You notice a big jump by midday. Now we're low to mid 70s. The pinks are mid 70 and higher dew points down into Illinois, and that trend continues into the evening. So we've had kind of a uniform increase in moisture across a good chunk of the warm sector. What does that look like in the vertical? Well, here's a Davenport sounding, which is located in east central Iowa on the Illinois border, essentially. This is like the soundings you saw from Topeka and Omaha. Vertical mixing, you're going to actually see moisture. There's higher moisture content above the surface than there is right at the ground. So the dew points would increase. And then in this case, the surface dew point increases, but notice the overall moisture content doesn't change a whole lot in the boundary layer. It just redistributes what moisture is there. So we've got large buoyancy, but the layer's relatively shallow. And this is typical of these sort of events. The deep layer wind fields are fairly weak. It's usually deep into the warm season when you see this stuff. There's a Lincoln, Illinois, same sort of thing. The moisture increases with height just above the surface. Same deal. We turn on the sun, turn on the crops, we redistribute the moisture, and some of the evapotranspiration may actually, there's a little hint of a stable layer right there at the surface, and that 70, whatever it is, mid to upper 70 dew point might actually be reflective of just a skin layer. But again, this is the kind of thing you can see. Now you might say, wow, look at all that cape. Boy, the cornfields are rolling today. Well, let's look at where this air came from over the previous week. Again, the pattern leading up to it. So I sort of sketch in loosely frontal zones. My red ones, I don't have any fancy software for this, so a red line is a warm front, and brown line's a dry line, and then cold front's blue. You'll get the picture here. And I'm going to look every 24 hours. So this is several days beforehand. Look at that. We have low 70 dew points 5 days in advance sitting across Illinois, Iowa. Wait a minute, I thought the corn did it all that day. Well, that air mass moves up into Iowa, Illinois. Oh, look at that, mid 70 dew points are present 4 days in advance in the same area. Again, it must have been the corn all that one afternoon. Low 70 dew point still sitting there, still hanging out on the old frontal zone, and then here's the day we were looking at. So again, people come up with all sorts of crazy claims like, wow, this, it has to be the corn dew points or whatever. You can track this blob of air for 2 weeks back down to the Gulf Coast. There's a little bit of augmentation. Primarily, it's air that's coming off a warm ocean basin. So I've seen many, many false claims regarding the source of this moisture and how rapidly it occurs. And some of it from professional meteorologists. So I won't name any names, but point is, I don't want you guys to do that. I want you to come up through the ranks and quit saying that stupid stuff. Look at the data, and you'll see that it's actually a lot simpler than some of the claims some people make. Okay, now, I mentioned a fun case we were going to have. I'm going to purposely not give you nearly enough information, but that's what makes it more fun. But I want you guys to think about the warm sector, sort of a general forecast for Kansas, Oklahoma in this case. And fortunately, looking at this crowd, you guys are not going to know this one. Okay, this is 12Z. Morning of. Now, I did take the dates off, just in case there's a cheater in here. Strong shortwave trough, northwest Mexico, Arizona. That might pique your curiosity. Belt of strong flow. You might think, wow, this looks kind of interesting. You especially might think it looks pretty interesting now. This ejects out over the high plains. Again, we talked about cyclogenesis a little bit, and you might expect a strong lee cyclone with something like this. Look at that, a whole chunk of 80, 90 knot, 500 flow, and looks like a pretty dynamic system. Here's 850 millibars. There's some moisture out over the high plains. We see some evidence of moisture, 50 knot southerly flow beneath southwest flow, 80, 90 knots. Sounds like a pretty interesting scenario. We'll make it even more interesting. Here's the sounding in the warm sector the night before. So you have large cape, nice moist layer, steep lapse rates, and this is just sitting there, just waiting. And now we had this big synoptic wave crash into it comes right out and interacts with this air mass. So again, what have I been harping on so far is don't make assumptions about what things are going to look like. Because if you make assumptions, you'd say, wow, this is going to be one of the bigger tornado days of the year. Here's that same location 24 hours later in the warm sector as the wave is ejecting. This is actually the Norman sounding. This happened here. Look at that. That was in the warm sector. It got worse in every way possible in 24 hours. The moisture decreased. The cap increased. There's clouds aloft. The surface temperatures are cooler. This one evolved almost completely backwards from what the storm weenie would want to see. Now, that's probably saved Oklahoma some trouble on this day because the wind profiles are very strong and indeed could have been fairly interesting. So I'll show a few radar images. These are about an hour apart. What did happen? Now, there was moisture on the high plains when this initially showed up. So we developed very quickly into the squall line. We'll talk about some of the stuff that goes into convective mode a few sessions down the road. But the idea is a quick transition into a line. Well, at least that looks pretty good. You would think big wave, 120-meter height falls aloft. I mean, this is going to persist all the way, out into the plains. Squall line goes toward the I-35, 135 corridor and disintegrates. It's sprinkled in Norman is all we got out of that system. And it's because of the sounding I showed you. So the point here is you have to look upstream. Again, you might make the assumption there's going to be a huge outbreak with this approach to this strong shortwave trough and strong cyclogenesis, but then look at what happened. And the point is this information was available in the upstream soundings. We went from 3,000 cape closer to 500. I don't think the standard playbook calls for a 2,500 joule per kilogram decrease in buoyancy one day over the other. The SIN increased. Order of magnitude, that's impressive. So again, you just have to think about it. This is a case, I'm trying to purposely show you cases that will hopefully get you thinking that don't just make assumptions. Assumptions get you in trouble. And I've done the same thing myself in my career, and I'm just trying to encourage you not to do that. And if you don't think that assumptions or poor reasoning can hurt, think back to my motivation, like slide 3, session 1. The 5-inch hail, 100-knot winds, no thunder, that could be you. All right, so the low-level moisture summary, it's a multi-day process. Again, none of these things are a big surprise. Where's the air coming from? What are the underlying ocean current characteristics? And then what is the character and the vertical extent in terms of the quality and depth of the returning moist layer? And of course, with mixing and evapotranspiration, you got to look at the vertical structure. You have to consider the structure of the temperature. Or if we get deep mixing, that's not going to allow the moisture to accumulate in the boundary layer. And so there has to be some sort of cap. And then, of course, what do the regional and local moisture sources look like that could either help or hurt, as we've shown. All right, so that's what I have for the first part. What we'll do here is take 5 minutes. I haven't punished you too bad tonight. So we'll make it a 5-minute break, and then we will resume, and we'll take a look at lapse rates and kind of try to tie this together in part 2 of this. So appreciate it, and we'll resume here about 8:15 or a couple minutes after. 2 here, start looking at the impact of lapse rates. Yeah, that's right. If you keep talking, there's a quiz coming up, and it'll be on stuff I haven't covered yet. Okay, so we're going to look at kind of the other half. Thermodynamically, we've been looking at the sources and the ultimate fate of moisture, all sorts of processes with the air mass modification over the ocean, adding heat and moisture over land. There's all sorts of complicating factors there, but then the other half of this is if we want large buoyancy, we need steep mid-level lapse rates. Where do those come from? So that's what we're going to talk about next. And if you haven't heard it before, the elevated mixed layer, a lot of times people just abbreviate that, the EML, so that's just short for not having to spell out this mouthful every time. Where does this come from? Well, again, the whole process works a lot like what's going on over the ocean. It's just the underlying surface. It's not water, it's dry land. So in this case, we've got strong daytime heating and mixing. We showed soundings that illustrated that week 1, and it's usually over the higher terrain. And the elevation of the terrain does matter because that tells you how deep the mixing in the layer is going to be compared to the other low elevation areas where the moisture sources originate. So again, it's surface heating over the plateau. So we're looking out at the areas out in Arizona, New Mexico, Colorado, northern Mexico, that area, and we have quite a few soundings to sample it. Okay, so the depth of it just depends on how warm is it aloft. I mean, the mixed layer is how much heat input do you have at the surface, and then how is it redistributed in the vertical. The only unique way to answer that question is to look at the data, and then of course, sometimes you have cooler profiles to start with. It does impact the depth of the mixed layer. All right, so we're going to do the same thing, just to make sure everybody knows where we are. I would figure with this bunch, you guys would know these, but we'll just be fair to everyone. We're going to look at a sequence of soundings across from Albuquerque to Amarillo to here in Norman, and look at the evolution of the elevated mixed layer, much in the way we were looking at the moisture return. Okay, so here's the evening before, and I've shown this sounding before. Somebody might recognize the date or be able to figure out why it might be relevant. This is Albuquerque. This is what is known as an elevated mixed layer. The elevated part is the elevated terrain. Notice it's just a surface mixed layer at Albuquerque, nothing special. The difference is when you come over to somewhere like Norman, is the surface at 850 millibars here? No, it's more like 975 millibars. So we're definitely at a lower elevation than Albuquerque. Now here's Amarillo the following morning. The flow is generally out of the west in that layer, and if you look at it, the lapse rates in that layer just below 500 millibars to just above 850 millibars are pretty similar. So what we're doing is we're transporting the mixed layer from Albuquerque out over the high plains. Well, here's the evening sounding. This is May 3rd, 1999 from Norman. And you might recognize one of the errors. I showed one like this in the first. This is a SON goes up into a not-so-friendly supercell thunderstorm anvil. No telling what happened to it. About 25 miles from a violent tornado at the time. But in this case, we've got a nice moist layer below, but steep lapse rates above. Here's the Amarillo sounding overlaid on that from the morning before. It's almost a dead-on match to the lapse rate. So we transported the lapse rates that formed previous days out over the high terrain, much like the moisture, except down below, we're at lower elevation, where's the air coming from? It's a veering wind profile. It's coming out of the south in the low levels. It's the moist profile that's Texas and the western Gulf Basin, which in this case, we're mid to upper 60 dew points. So we've created large buoyancy by superimposing steep lapse rates on top of a moist boundary layer through differential advection. So what I'm going to do is take a little bit closer look at the elevated mixed layer, and I think it's kind of an interesting way to look at it. You can do this the same way as you can with the moisture return. You just consider what are the typical mixed layer profiles look like out there, and then what does that mean downstream? And again, I give the reference to the Lanici and Warner paper, which many of you probably have never seen, from the early 90s. It was probably the best climatology that I've seen. Now, the important thing here is I focus on their figure 6 here, where I'm looking at, when I talk about these potential temperature values, it's what's the value of a dry adiabat in that mixed layer? Because these are dry adiabatic layers, and what's the value of that dry adiabatic layer as we go from April to May to June? How much does it warm? Okay, so this is their climatology, and this is from April. You get Potential temperatures 36 to 40 C. I'll illustrate this in a second on sounding. As we continue into May, you warm to 40 to 44 C, so it's substantial warming, and then June 48 to 52 C. So that's quite a bit of warming and that's, again, the seasonal warming of the surface temperatures over the elevated terrain. Okay, what does that look like on a sounding? Well, here's that Albuquerque sounding again. The potential temperature, it's about 38 C. That's just the temperature if we continue dry adiabatically down to 1,000 millibars. So it's just another base thermodynamic quantity. That's how we label the dry adiabats, is what that temperature is of that adiabat where it crosses 1,000 millibars. So in this case, that would be a layer 38 C, is roughly what it comes out as. Okay, we'll put it on the sounding from Norman. I'll show this one some more in the next example as well. Here's the typical mixed layer for April. Now this is out over the New Mexico area, and this is a potential temperature early April, what's typical. Here's what it looks typical of early May. Here's what's typical of early June. So you see the seasonal progression, how much the elevated mixed layer warms. And you can see in this case, for that sounding in May, it would have been completely different if you had an April type mixed layer atop that moist layer, because that's a mid to late May sounding in the background. And then you look at the actual May case, it's actually fairly close to the climatology for May. So that's a pretty typical looking moist or elevated mixed layer on top of a moist boundary layer here at Norman. All right, so what should you look for? I mean, one thing is, look at the surface temperatures just out there, Salt Lake City, Durango, Colorado, Albuquerque, Flagstaff. If it's way above normal out there, they're having record highs, that's going to say something about the warmth of the mixed layer that's likely to come east over the plains. If it's cooler than normal, it may or may not, it may mean a deeper mixed layer. It might mean that you don't have as much of one. There could be clouds, any number of things can be happening. You just have to put all the information together. And the details do matter. And then, of course, the EML doesn't just magically appear the morning of an event. You can trace this back for days. It's just like the moisture return. You should be able to anticipate this days in advance. So hopefully this should be becoming clear right now that if you want steep lapse rates atop a rich moist boundary layer, there shouldn't be any big shock. You could see this 3, 4, 5 days in advance, this pattern setting up that's going to not only generate the moist layer, generate the lapse rates, but transport them in a differential sense to the same locations. All right, now let's look to the north. We've been kind of southern plains biased so far, so I'll show you that amazingly this does work in other places. We'll look at Denver, North Platte, and Omaha, so we'll continue across on a different trajectory, more typical of later in the spring. Here's the evening before. Now, Denver, again, same elevation roughly as Albuquerque, very deep surface-based mixed layer, all the way up to 500 millibars, dry adiabatic. And it's a dry mixed boundary, and there's a little bit, might have even been some high-base convection with that sounding. Here's North Platte the following morning. So the flow's coming out of the west-southwest, that's essentially from the Denver area. And you notice the lapse rates are almost identical up above the surface. However, the only difference is where the air is coming from somewhere else in the low levels in North Platte. And then we continue over to Omaha the following evening. So this is a full 24 hours later, and we still retain that steep lapse rate layer in the mid-troposphere. The only difference, we brought in a moist layer from further to the south and off to the east of where the lapse rate plume originated. All right. Just again, if I've offended anyone in the northern plains, we'll keep going further north. Amazingly, it even works at Rapid City and Aberdeen. Here's Rapid City. Same sort of thing. Looks pretty similar. This is the same day as the Denver example before. Fairly deep mixed layer. It's clearly surface-based. It got warm there. And then we look at Aberdeen. So if we've got Aberdeen the next morning, we've got that same lapse rate. So you've got a very warm, elevated mixed layers overspread Aberdeen, much further to the east. Now the interesting thing is, this is why, again, you have to look at the details. This is the sounding from the evening before at Aberdeen. Essentially your classic loaded gun, fairly steep lapse rates, large buoyancy, reasonably strong vertical shear. But if you go back to that sounding, that's what happened overnight. So the change in this case was actually the moisture didn't improve and the cap got much stronger. So it has an impact on the following day's convective potential. And in this case, it actually limited severe thunderstorm development to the south. Okay, so differential advection is what we're really getting at here. I've mentioned it several times. So we get steep lapse rates from the high terrain to the west is where they typically form. Moist layer in the low levels from the Gulf of Mexico or the Caribbean basin to the south creates the loaded gun. And again, it's just a classic example. This is the May 3rd, the Albuquerque sounding from the evening before in purple combined with the Norman sounding from 0Z the evening of the event. Again, you can see that layer is almost identical, the elevated mix layers, to what was sitting out at Albuquerque the evening before. So hopefully this sinks in that it's important to look at the source regions for your lapse rates and your moisture. And again, it's just highlighting that that's the old mix layer sitting atop the moist layer further east and south at a lower elevation. Now, again, since I was nice to the northern plains, let's not ignore our friends out east. The elevated mix layer can make it pretty far into the eastern U.S. on occasion. This is the 700 to 500 millibar lapse rate plot from the SPC mesoanalysis. Those values over Tennessee, Kentucky are 9 degrees C per kilometer. That's close to dry adiabatic. Goes all the way to the Atlantic coast. This is the morning of the June 29th, 2012 big derecho event across Ohio into the D.C. area, right on the north fringe of the steep lapse rate, large Cape environment. So it just goes to show, even though it wasn't a tornado event, you can track this plume back to the Rockies over the course of a week. You watch the lapse rates gradually spread eastward and then southeastward around the ridge. Okay, and I highlighted the cap earlier. The base of the EML, that transition zone between the elevated mix layer and the moist layer below, that's what we call the cap. It's usually a stable layer. But then again, the degree of cap, you want some cap if you want more isolated, discrete storms. And again, in a few weeks, we'll talk about that in more detail. But it's not simply how warm is the elevated mix layer. How rich is the moisture? How strong is the heating and mixing in the warm sector down below the cap? All of these things play together. Okay, so we're going to look at a case now. We're going to kind of step through, sort of tie together the moisture, the lapse rates, and look a little bit at convective initiation and some things you probably ought to consider when using some of the information presented here, i.e. the SPC mesoanalysis graphics. Okay, here's the morning of May 19th. You guys, at least locally, if you've been around for a couple of years, you'll remember that. This is the Shawnee EF4, and there was another large tornado at Kearney, I believe. So there were two dangerous tornadic storms later that afternoon and evening. Steep lapse rates all over the southern plains. There's a little bit of a indentation there across southern New Mexico. We'll talk about that here in a second. So I go through kind of the evolution, and this is every 3 hours. The lapse rates stay over the warm sector. Now you notice there's this tendency for weaker lapse rates to come in from the southwest. Well, it may or may not matter. Again, this is where you have to consider, first of all, where does that signal come from? The lapse rates are steep where it's moist, all across the I-35 corridor. And they stay relatively steep. Even where the lapse rates weren't as steep down there in West Texas, it's still near 7 degrees C per kilometer, which is conditionally unstable. Okay, well here in the morning, if we look at the actual upper air maps, we're going to look at, this is just 12Z, 700 millibars. It's cooler northern New Mexico than it is southern New Mexico. So there's a tendency for the warmest core of air and the warmest part of the elevated mix layer. Usually 700 millibars is near the base of that elevated mix layer. You see the corridor of plus 12 temperatures out at Norman and Fort Worth. So the core of the elevated mix layer is out over the plains as of morning. But if you look out here back in New Mexico, see that strong thermal gradient? I mean, the temperature, it's in the upper minus teens in Albuquerque, and then it's a minus 8 or 9 down toward El Paso. There's a mid-tropospheric front there. So it's warmer down to the south, and that's on the south fringe of the mid-level jet. When you look at the soundings, the sounding in the foreground in the green and red, that's actually Midland, but the upstream sounding is El Paso. So you notice it's actually a more stable profile at El Paso, and it's a reflection of that mid-tropospheric front. And the mix layer is not as deep. So you wouldn't be surprising to see some stabilization in the mid-levels as you bring that air from southern New Mexico out into West Texas. It's just, it didn't go any further than that during this case. But it's just something, if you want to explain why that odd configuration in the lapse rates, it's in the observed data that morning. Okay, so let's look in the low levels. This is just the standard surface temperature dew point analysis. We've got a low over the high plains. This is at 12Z, 15Z, 18Z, okay, we're getting pretty hot in northwest Texas. Those temperatures are in the 90s now, so we should be getting deep mixing, upper 60 dew points out near I-35. You would think this looks like a pretty interesting scenario, and then here we are at 21Z. Temperatures, I believe that little spot, if that's believable, is near 100, just out toward Vernon, the lovely spot of Vernon. And we've maintained upper 60s just to the east of Interstate 35. Low-level lapse rates. During the day, same kind of thing. We're getting deep heating and mixing back in the dry line. When you see these 10 and 11 degree lapse rates, that's a reflection of even the superadiabatic contact layer. So that's greater than dry adiabatic lapse rates through the whole 3 kilometer deep layer. So that just tells you there is strong heating and vertical mixing going on back there, but it doesn't extend very far into the moist air, closer to Interstate 35. All right, so we look back at this. There are other ways you can look at this information. This, because if you look at this, you'd say, hey, it looks like there's a front. Some people might be tempted to draw that as a cold front across northwest Texas. They say, well, look, the temperatures drop off as you're going into Mexico, and it's right there. The thermal ridge is right on the wind shift. Sure, is that a cold front? Well, if you actually plot the potential temperatures, all you're seeing is the influence of elevation. The terrain slopes up to the west, so the potential temperature field is relatively flat. The only strong frontal zone is way up in the north edge, up toward Goodland. You can see evidence of an actual cold front up there. And in this case, the mixing ratio, if you guys remember, is a function of pressure, so this accounts for elevation. So if you want to normalize to elevation, mixing ratio might be a better way. And we have this again on the mesoanalysis page, just a different way to look at the same thing. The pattern is similar, but just so in this case, this is perhaps a more meteorological way to look at the data than just simply the surface temperatures and dew points. All right, now let's have some fun. All this lapse rate moisture stuff, do we get storms or not? Where do they form and why? This is in the morning, 2500 Cape just to start the day. This is the ML Cape profile, so that's pretty big for 12Z. Everything's blue, so there's strong convective inhibition all over the place. 15Z, blob of higher Cape, a little bit to the north, still capped. Okay, first sign toward midday, the cap is supposedly weakening up toward northwest, north central Oklahoma, still pretty strong to the south. Okay, this is a case where we had soundings, so we had some special ones were launched by the local office in Norman, and Lamont, again, will launch one. So this is the sounding from Norman, fairly unstable, typical loaded gun profile, still looks like it's reasonably strongly capped, but this is only early afternoon, so we still have some heating and mixing to go. And there's Lamont, pretty similar profile, just slightly cooler, but the buoyancy is about the same, the cap's pretty similar. So these are kind of our snapshot in the warm sector. I don't think looking at those two, you'd really come up with a big difference about where storms would form, favoring north versus south, but the mesoanalysis graphics clearly favor north. And just to overlay them, just so you can see, not too different. And if anything, even though Lamont is a little cooler in the mid-levels, the whole sounding shifted a little bit to the left, so it doesn't make that much difference in the net. Okay, 21Z. We're capped in central Oklahoma, a min in the buoyancy field. Now again, those of you who remember what happened might wonder, why would that be the case? Right in here. So we highlight the area where the SBC mesoanalysis graphics, they're never wrong, right? Never. And there's no reason to look at any data. That's why I've showed all these actual soundings. So there's no reason to look at them. Let's see how realistic that looks. Because again, now I will ask a question. Does anybody know where the moisture above the surface comes from in this analysis? Surely somebody knows. The RAP model, yes, the RAP model is the source for the moisture profile above the surface. We don't have any other information during the day except for the occasional sounding. So in general, we have to rely on that for profiles, and we're looking at the 100 millibar mean parcel, so it's going to be sensitive to that moisture profile in the model. Well, what does this look like if we do the surface-based CAPE? And again, normally you hear us reference ML CAPE, but in this case, the surface parcel, this is 15Z, 18Z, 21Z. Look at the difference in the analysis over central Oklahoma. There's a max in the buoyancy according to the surface parcel, right where there was a min for the ML parcel. that should tell you something is up right there, that perhaps one of these two is not correct, because this is mid-afternoon, we should have a nice mixed profile. You wouldn't expect to see these kind of differences. Typically, surface-based CAPE would be a little bit larger, but the overall pattern would look the same. In this case, they're pretty markedly different. Well, again, observed data usually answer these questions for us. This is satellite images. That's midday, early afternoon. This is at 19:55, so this is an hour before the soundings. Storms are already forming in central Oklahoma where the min in the buoyancy and the max in the cap was supposed to be. Again, if you just get your head stuck in your laptop or whatever it is you're doing and you don't look out the window, you don't pay attention to the actual observations, you might say, well, gee, the only storms are going to be up north. Why would I expect anything down here? And sure enough, it explodes down here, and the strongest tornadoes of the day are with those cluster of supercells. So again, always check the observations. There's no reason not to. When you have soundings, by all means, use them to compare. And so there's a whole bunch of stuff you need to do. And I'm going to say this probably 1,000 times as we go over this. Look at the observations, piece together a conceptual model, look at the source regions for everything. And if you can do all of that, forecasting's still tough, but you will set yourself up for far more successes than you will if you live completely in model land or you just blindly accept all the stuff you see coming across, on your internet, wherever you're getting your information sources from. Okay, now I do want to at least acknowledge that there are other ways to get steep lapse rates that don't necessarily involve the elevated mix layer. I'll show a quick case here where that did not appear to be what was happening. It's actually the one from mid-December. We had the weak tornado or two somewhere around here, which is a little bit anomalous. I think it was back on the 14th of December. Here's a case where 700 millibars, this is in the morning. Wave progresses, or the low moves out over the high plains. So in this case, compared to the other ones, it's not nearly as warm. There really wasn't much of an elevated mix layer as denoted by the relatively cool 700 temperatures everywhere. And I'll show you the soundings that match up with this. And then we continue at 500 millibars. The trough itself is actually well out into the plains by 0Z. And notice the temperatures at Norman have cooled from minus 14 to minus 19 during the day. Okay, so here's the sounding. The one in the foreground is the Norman sounding from 0Z that evening. Lapse rates are relatively steep. It's not a particularly warm, sort of moist for December, but not particularly warm, but the rest of the profile is fairly cold. It's minus 19 at 500 millibars. That's relatively cold for a warm sector here. In the background, that's the 12Z sounding. So you can see there was a little layer around 700 millibars with some sort of steep lapse rates, but there's really not what we call a classic elevated mix layer available. Okay, well, where did these steep lapse rates? We still have fairly large buoyancy. Where did this come from? Well, that's the overlay of the Norman 0Z sounding. In the background is the Amarillo 12Z sounding. It's a profile near the cold core low, parcels with a long history of ascent. So what does ascent do to the profile? It cools it. Over time, you're basically recreating the cold pool with the mid-level trough as it progresses eastward. So it's not just purely advection. But also notice in this case, look at the wind profiles. They both show that veering in the low levels and then solid backing as you move up through a deep part of the mid-troposphere. Well, from thermal wind arguments, a backing wind with height, cold advection. The same sort of thing was present in Amarillo. So we're basically bringing a cooler profile out. This is one of the relatively rare cases where there's mid-level cold advection is what actually may have helped with a lot of the destabilization. However, you don't see this particularly often with big tornado events. Some severe weather, yes, but usually the big events don't look anything like this in the warm sector. So, but you can do it. It's not, there's a number of ways. Again, get your hands dirty, roll up your sleeves, and look at the data. All right, well, that brings us to the end of the lapse rate stuff. I said it should be a little bit shorter tonight, and it looks like it's definitely 15, 20 minutes shorter than last time. What we're going to do next, this will be in the next session, which is next Tuesday evening. We're going to look at the impact of ascent on profiles and sources for lift and how that relates to convective initiation. And then we're also going to look at things like outflow boundaries and what they do locally to vertical shear profiles and what's a good outflow boundary and what's not so good outflow boundary. So we'll talk about and show a lot of cases there. And If there's any questions, I'd be happy to take them. Otherwise, I appreciate it, and we'll meet again next week. So thanks, everyone.